So now third application of Gauss theorem, that is a field due to a uniformly charged thin spherical shell. Suppose there is a spherical shell which has got charge Q and radius is here, suppose it's R. Now if you want to calculate electric field intensity at a distance R here, it means here we can take R is greater than R. So if you want to calculate electric field intensity at this point, by taking this radius R small r, we draw a sphere that is known as Gaussian surface. And Gaussian surface is drawn in such a way that it does not pass through this charge or through this shell. And it is enclosing completely the shells. And now we just take area vector at any point. Suppose you have taken area vector is here, that is ds, and electric field is also radially outward. So we can write flux is equal to E dot ds is equal to E ds cos theta. Here theta is equal to 0, so we can write E ds, and here we can write E is constant at every point on the Gaussian surface. Here we write integration of ds, that is a whole surface, so that is E into 4 pi r square. Now according to Gauss theorem, this flux can be written E into 4 pi r square is equal to Q by epsilon naught net charge enclosed by this Gaussian surface. So in this case we can take E is equal to Q by 4 pi epsilon naught r square. Here vector, this is r unit vector. So this vector is radially outward. So this is the electric field intensity at any point at a distance r from the center, which we have calculated by using Gauss theorem. But see, this electric field intensity is equal to the electric field intensity due to point charge. It means we can say this spherical shell is behaving as a point charge. So in the first case we have seen here, when R is greater than R, it means point is somewhere here, and we calculate electric field intensity at this point. We have got E is equal to Q by 4 pi epsilon naught r square. Now if you take R is equal to R, then electric field intensity will become Q upon 4 pi epsilon naught r square. So on the surface of this shell is this much. Now if you are calculating third point here, R is less than R. It means point is somewhere here, R, and by taking this you are drawing here the Gaussian surface. You will see here all the charge is outside this Gaussian surface. So no charge is enclosed by this Gaussian surface. So if you are drawing Gaussian surface inside the cell, so net charge enclosed by the Gaussian surface is 0. Therefore electric field intensity inside the cell is 0. So when R is less than R, we will be getting E is equal to 0. So we can show this variation of E from the center of the cell with the help of the graph. We can draw the graph like this. This is your x-axis, this is y-axis. Here we have taken E and here is R. This is O is the center of the sphere. When we start moving from the center of the spherical shell, so at R is equal to R, electric field is here this much, maximum, that is equal to this much here. When we go beyond this surface, electric field intensity reduces here because E is proportional to 1 upon R square. So the graph is like this. So outside here, that is E is proportional to 1 upon R square. So this is the variation of electric field intensity with the distance R from the center of the spherical shell.